Okay, thank you for the introduction, Wojtek, and thank you to all the organizers for having me and all of you for showing up. So I just emailed my lecture notes, so they'll be appearing. I've organized them into 4 lectures, but given over 5 one-hour slots. So basically, we'll do 1 1/4 time slots for each lecture. Let me give you a little bit of a preview of what I want to convey to you during this course, and then we'll get into the material. So, or I can tell you what the lectures are. So the idea is going to be to look at combinatorial problems from the perspective and point of view of statistical physics. And hopefully by the end, you'll see that this is a nice way to look at things. Maybe there's some tools or some ideas that will come in useful. But I'm not assuming you know anything about physics. I definitely don't know much about physics or anything about statistical physics. So I want, part of the goal is to convince you that this is a cool subject. It's not so far from things you know. But the perspective is definitely different. And so that's actually the first lecture. Is going to be about how do statistical physicists look at things, what are the objects they use, and things like this. The second topic will be about how do you translate between combinatorics and statistical physics. And I'll give you some dictionary of terms that you can go back and forth. The third topic will be a particular tool from statistical physics we'll use. And then the fourth topic will sort of be the fun application. And the application and what we're working towards will be talking about triangle-free graphs. And this is, maybe the first topic in extremal combinatorics with Mantel's theorem. But it turns out there's like some still very interesting open problems related to triangle-free graphs. And you can view these open problems from the perspective of statistical physics that we'll talk about in the first 3 topics. So that's the plan, and please do ask questions. I'll be coming to the exercise sessions. We have lots and lots of exercises for you to do, because with all things, like especially something new, you really have to get your hands on the objects to start to understand it. Okay, so good. So today's lecture is about, I guess, fundamentals of statistical physics. I don't claim to cover all of statistical physics. Really, I want to focus on a few models and a few topics that will be most relevant for us in combinatorics. So first we might, what is the point of statistical physics? So the goal is to understand, okay, this is my interpretation, but understand how microscopic interactions lead to, I don't know, large-scale behavior. Okay, and so what do I mean by this? I mean, imagine you know something about the physics of like air molecules or water molecules, and you know something about temperature. Can you predict the behavior of the gas that's in this room, or a bucket of water that's sitting in the room as temperature changes, just by knowing microscopic interactions? And so this is actually like some long-term program, dates back at least to Boltzmann, to come up with a connection between microscopic interactions and global large-scale behavior. And in particular, things like freezing, how a liquid freezes to a solid, or a gas, vaporization, how a gas or a liquid turns into a gas when you heat it up. Also, we'll see magnetic material. So maybe when you were a kid, you had a piece of iron and you ran a current through it. But even after you take the current off, it's still magnetized. So things like this. And the goal of statistical physics is to come up with some nice mathematical model that maybe is not completely accurate, but exhibits this, you can change the microscopic behavior and see changes in the global behavior. And so that's what we'll talk about. But one big point I want to talk about today is the notion of phase transition. So if you notice, the things I talked about actually are things that change. So as you change the temperature, the state of a fluid changes. As you change the temperature, this property of the magnet remaining a magnet actually changes. If you heat it up, that won't happen. And so today I want to give you actually 3 different definitions of a phase transition. And all of these 3 definitions will be useful actually when we apply things to combinatorics. Good. So we need to start with some definitions and some math. And so I want to talk about the objects of statistical physics. And the main objects that we're going to work with are something called a Gibbs measure. That's a probability distribution. And a partition function. That's, I guess, a number or a function. But it's the normalizing constant of the probability measure. And these are the main things that we're going to be working with through the course. And so let me start sort of formally. So we have a set omega of configurations. So think of this as like, maybe you have a graph G, and then vertices and edges, and then omega might be 0, 1 to the v. Okay, so we're going to assign a 0 or 1 to every vertex of the graph. Or maybe omega could be, maybe you assign a color to every vertex of a graph. Okay, so think of the set of configurations as quite large. And often, they, for our purposes, they'll be associated to assignments of some small alphabet to the vertices of a large graph. And then you have an energy function. We'll call it H. And so H takes in a configuration, and it outputs, let's say, a real number, but it might be plus infinity. Okay, and then you have a parameter, beta. Let's say it's real, and this is called the inverse temperature. And from these objects, we can define a probability distribution. The probability distribution will be, let's call it mu g beta. So beta is this parameter. G is this underlying graph we have. And we look at a configuration sigma in our big set. So this is like some assignment of 0 and 1 to the vertices of the graph or colors. And this is going to be e to the minus beta times the energy. Okay, so we penalize things with high energy. In particular, if this h took the value plus infinity, this thing would be 0. Now, of course, this is not a probability distribution, right? I mean, it could be maybe, but it's unlikely to be. And so we need to divide by something to make sure this, if we sum over everything, it sums to 1. And the thing we divide by, the normalizing constant, zg of beta, this is called the partition function, so which is zg of beta is just the sum over all configurations, e to the minus beta h of sigma. Okay, so this is the Gibbs measure. This is the partition function. And we'll have lots of examples. Yep, question?
So what is this letter, like in the subscript?
Oh, just G. Just saying that, yeah, because we might want to change the graph and think about different graphs. Okay, so this is a short course, but in the notes there's some references. You could ask, why do we define it this way? And it's a very good question. you can, there's some different ways to derive this and different ways people came up with. One way I like to think about this is, and we'll talk a little bit about this more, but a probability distribution of this form has a very special property. It's the maximum entropy distribution subject to the constraint that the expectation of h under this distribution is some value. Okay, and so some of the exercises I have for you are about maximum entropy. There's plenty to read about, but that's just one hint about why this is the right form of a distribution. It doesn't matter. It could be either, but I mean, you could also say beta is always positive and then bake the sign into h. But for the moment, sometimes I'll want to switch the sign of beta. So let's say it could be anything. Okay, so this is the general setup, but I think it's good to have a couple examples, and these examples will be important for us. Example one, maybe this is the first, in some sense it's the first model where there was a phase transition proved. It's called the Ising model. And so I need to tell you what the configurations are, and I need to tell you what the function h is. So the configurations are plus minus 1 to the v. The Ising model, I'll say it's a model of a magnet, and you can imagine that like molecules point in a certain direction. They're aligning with a magnetic field, but this is a toy model where you can only point up or point down, plus or minus. And then h of sigma is the sum over the edges of the graph, uv and edges, sigma u, sigma v. Okay, so this is, what is this? You're looking over all the edges in your graph, and you're just giving a plus 1 if the spins agree, and a minus 1 if they disagree. Okay, maybe I'll put a minus here. So now you have a minus 1 if they agree, and a plus 1 if they disagree. And so the distribution, mu g beta, if beta is positive, it favors configurations with monochromatic edges. Okay, so you get an exponential boost in the number of edges that get the same spin, we call it, the plus or the minus 1. So one thing you can ask is, and this is a term we'll use, a ground state is a maximum probability configuration. So what are if G is connected here, what are the ground states? They're the monochromatic configurations, just the all plus and all minus. And so in a sense, you can think, what is this inverse temperature parameter doing? If beta is 0, right, then you're doing e to the minus 0. So actually, you're just a uniform distribution. So you're just picking independent, probably a half spins at each vertex. That's something we understand very well, independent random variables. And if beta tends to infinity, then you're just picking one of the two ground states at random, either all plus or all minus. And so the interesting part about statistical physics is trying to understand this interpolation. You're interpolating between pure entropy, all the different possible configurations equally likely, and optimization. And so you might want to know for a given graph, if beta is large but finite, what does a typical configuration from this distribution look like? Okay, so that's example number 1. Example number 2 that will be very useful is something called the hardcore model. And this is a model of independent sets in a graph. Okay, so the configurations are, let's say, 0, 1, to the v. So 0 meaning not occupied, not part of the independent set. 1 meaning part of the independent set. Okay, and the energy function is going to be, let's say, product over uv edges, indicator function that sigma u plus sigma v is less than 1, less than or equal to 1, right? So I don't want 2 1s across an edge because that's not an independent set. And so if you, actually this should be, sorry, I'm thinking. This should be, okay, sum over the edges. Let's say plus infinity times the indicator function sigma u equals sigma v equals 1. Okay, so we get a plus infinity if we violate the independent set condition. And then maybe we have like sum over v indicator, or just sigma v. So I have 2 terms, one that forbids stuff that is not an independent set, and another configuration that just is counting the size of the independent set. This is a little bit awkward way to parameterize things. And so the better way to parameterize this, let me just write it in the corner, is so mu g lambda of an independent set is lambda to the number of vertices in the independent set over zg of lambda. And here zg of lambda is the sum over all independent sets in the graph, lambda to the size of I. Okay, and so beta is something like log lambda here, if you want to do this parameterization. So this is the partition function of this hardcore model, but in graph theory, this is just the independence polynomial. This is a polynomial in the parameter lambda, but this is the probability distribution for which it's a normalizing constant. So one thing you can say, you actually know this object already. If you plug in lambda equals 1 here, then z just counts the number of independent sets of the graph. Okay, so this is some generalized form of counting these partition functions. And if you have lambda equals 1, then the probability distribution is just a uniformly random independent set in the graph. Yeah? The signs? Oh, you mean right here? I'm saying you get a plus infinity if on an edge they both take the value 1. So plus infinity is bad, right? E to the minus plus infinity is 0. And so you're forbidding any configuration where there's a single edge that both have 1s, which is exactly the independent set constraint. I mean, if you like, just think about this formulation where you only are looking at independent sets. Okay, good. So these are the basic objects, and you can define these models. There's many, many different models you can define. You can think of lots of different functions. You can have q spins instead of 2, and things like this. And then you can talk about different graphs. Okay? And so that will be part of what's interesting here is that in different fields, you might be interested in very different graphs. And so in statistical physics, they want to talk about reality, like this room we're in, the gas in this room, or maybe some two-dimensional thing there. And so in statistical physics, one set of graphs are like lattices, portions of ZD or other lattices and things like this. In computer science, the graphs that might be interesting often are random graphs. And in combinatorics, often the way we think is in terms of like worst case graphs over some big family of graphs. And so this perspective is very, very different, the kind of graphs that you might be interested in here. Let me quickly show you one slide from the lecture notes. Okay, it will come up. I just want to show you some simulations of these different models on boxes, lattices, just to give you a feeling of what they look like. Maybe I should. You think it's my computer? Okay, it's not so critical that we see the picture. I can describe what the picture is. I'll do like a real cartoon version. And so here I'm thinking like I have a portion of, let's say, Z2. And let's think about here we go. Thank you. Okay, so the first two pictures are with this hardcore model. And I'm taking portions of Z2. And the white squares are unoccupied vertices. And the red and blue squares are occupied vertices, but on the even or odd sublattices of Z2. And I've done two different simulations, one where I took lambda, which is called the fugacity, but just a parameter, lambda fairly small, and on the right, lambda much larger. And you see definitely some difference in the picture, right? In the first case, the red and blue roughly look random. If you really zoom in, and you can on the lecture notes once you look at them, and zoom in, like locally, actually, things line up. Like you see reds near reds. But then if you zoom back out and look globally, if I like point to the left-hand corner and you see some reds and blues, it really tells you very little about far away whether a certain square will be red or blue or something like this. On the other hand, on the right, there's something very different going on. And what has happened is that somehow the model, the probability distribution, has picked one of the colors and globally they've agreed. And if I did this simulation again, it might be mostly red with some blue islands. Okay? And the physics intuition behind this is that what we've seen is some freezing phenomenon. That we've gone from a state where there's a gas to a state where we're in a solid, like a crystal, where the lattice is this crystal, the sublattice. Yeah.
In the hardcore model that you've mentioned, we only have occupied or unoccupied. So what does even occupied and
Yeah, exactly. So if I had just shown you occupied, like I had black squares, it would just look like a bunch of black squares. But something has happened. And the something that's happened, you need to look at the graph and say there are some, on the Z2 lattice, there are different types of vertices. There's two sublattices. And when I look at which ones are occupied, then I see this dramatic phenomenon. Yeah. So, OK. And here's one other picture. This is not the Ising model, but something called the Potts model, which is just like the Ising model. You favor monochromatic edges, but with 4 colors in this case. It could be any number of colors. And here, I'm changing beta, this inverse temperature. And when beta is small, we're close to this independent case. Again, like locally, blues like to be next to blues, and pinks like to be next to pinks. But globally, it just looks like something random. On the other hand, when beta is very large, it's picked one of the colors. That color dominates throughout the whole graph. And then there's some little defects here. Okay? So really what I want to convey to you in this whole course is take this picture, think about it, have that in your mind the whole time. But it turns out in lots and lots of combinatorics problems, there's something qualitative very much like this going on. But we don't really understand quite the transition between the two. Okay, so this picture is really the main thing I want you to keep in mind through the talk. Yeah.
Should I be thinking of high lambda as being bigger than 1?
Not necessarily, no. 1 is not actually special from a physics point of view. For combinatorics, it's special because it's counting, but it's not special here. So I mean, in this case, high is like, I think 3.7 or something, bigger than 3.7. But if D was like 1,000, then high would be like 0.2. Yeah, the dimension, yeah. OK, so good. So what I want now to do in the rest of the time is to come up with a mathematical formulation of what it means to transition between the picture you see on the left in both cases and the picture you see on the right. So we want to say that some phase transition occurred, but we need to come up with definitions. And so that's what we'll do. And yeah, and first I'll show you some like nice identities that we'll use a lot. OK, so one thing I want to convey to you is that, and I'll put this in quotes because this is not something mathematical yet, but the partition function contains all the interesting information about the model. OK, so the partition function has some like mild sounding name is just the normalizing constant. But in physics, somehow understanding the partition function is what they mean by solving a model. If they can understand to decent accuracy the partition function, they think they understand the model. And I want to explain why that's true. OK, so if you, let's say you, and I do recommend this, let's say you coded up one of these models and you wanted to like run some simulations and see things. One thing you might do is to calculate some statistics about the model. Maybe in the easing model, you would say, well, if I pick this parameter, how many monochromatic edges do I typically see? What's the mean and variance of the number of monochromatic edges? Or in the hardcore model, you might say, like, what's the typical size of an independent set I see, and how does it fluctuate? OK, so you would want to compute statistics. It turns out that the moments of the random variable that is the energy, so in the easing case, the number of monochromatic edges, in the hardcore case, the size of the independent set, actually are given by derivatives of the log partition function. So let's see. So here's an example. So OK, so derivatives of log z are they're moments, but they're actually something called cumulants of h. So remember, h defines the model, but h is some function of configuration. So you can also think of h as a random variable under the model. OK? Cumulants, we'll talk about cumulants, and I've written about them in the notes. Cumulants are like moments, but in a different basis. So the first cumulant of a random variable is the mean. The second is the variance. And then the third is like the third cumulant, and so on. But for a lot of, in a lot of ways, they're more convenient than moments. So for example, characterization of a Gaussian random variable is that all the cumulants past 2 vanish. And you can show convergence to Gaussian by showing higher cumulants vanish. OK, so let's look at this. So let's say we want to look at expectation under mu g beta, right? This is our Gibbs measure of h of sigma. OK, so let's just write what this is. So this is sum over all sigma, h of sigma, times the probability that you pick sigma, which is e to the minus beta h of sigma over z. OK. Z is just, this is Z of beta. Z is just a constant, right? So we can pull this out. So it's 1 over Z. And then what is sum over sigma h of sigma e to the minus beta h of sigma? Well, this looks a lot like a derivative, right? If you differentiate in beta, okay, you get a minus 1, but then the h comes down. So this is, so minus 1 times the derivative in beta of, well, it's the derivative of this sum over sigma, e to the minus beta h of sigma. That's z. So z of beta. Okay, so I did that kind of quickly, but you should do this yourself and check. But now what do I have? I have z prime over z. So this is minus 1 times log z prime. Okay, so up to the sign, the first derivative of log z is the expectation of h. Now the way I've defined the hardcore model, it's a little bit different because we don't have e, we have just lambda to the size. But we can write expectation over lambda, size of independent set, is lambda times log z prime. Okay. So the first derivative gives you this expectation of the energy, which is some interesting statistic about your model. If you, I won't do it right now, but if you take the next derivative here, okay, you get the variance. So variance of h, and you get another minus 1, so the minus 1's cancel, is log z double prime. So take 2 derivatives in beta, and you get the variance. Okay, and these are just basic identities, but we're actually going to use these throughout the week. But it's partly for this reason that understanding the partition function tells you so much about the model. You're really controlling a lot of things. One way to think about it is, the partition function is almost like a moment-generating function. And so if you have control on the moment-generating function of a random variable, you know almost all you want to know about it. Okay, so that's one thing. Good. So I think I want to define what a phase transition is. Okay. Oh, one more thing. Good. So the other important perspective that statistical physicists have is they think a lot in terms of correlations. So in combinatorics, we might see some set of objects, and we might think, like, how many of them are there? What's, optimizers? What's the typical structure of one of these objects? In statistical physics, the way they think almost all the time is they think about this Gibbs measure, this distribution over this set of objects, and they want to understand how correlations behave. And I think this is a really powerful way to think. Like, always think, how do correlations behave in a random object from a certain distribution? And what do I mean by correlations? So the easiest way to define it is something called, in physics language, it would be called like the 2-point correlations. There's higher correlations, but 2-point correlations is fine for us. And it's the following. So you have vertices VW in your set of vertices in your graph. And let's say kappa VW, so this is some measure of correlation, is going to be mu VW minus mu V mu W, where mu V is just the expectation under the Gibbs measure of the spin value at V. So in the hardcore model, this is just like the probability that this vertex is in the independent set. In the easing model, the way I've defined it these are just 0, right? Because there's symmetry between plus and minus. Okay, so this would be called the marginal of V. And then mu VW is the expectation of sigma V, sigma W, the product. Okay, and so this 2-point correlation function is really just the covariance between these two spin values. If you were talking about independent random variables, of course this would be 0. And so this correlation or this covariance measures how far you are from independence. Good. And so one thing we're often interested in is exponential decay of correlations. So remember in the pictures, what we said was if you look very closely, like blues tend to be near blues. And so what that means is like for vertices close together, we expect the correlations to be high. In the hardcore model, the correlations for neighboring vertices are very high. If this guy is 1, the neighbor cannot be 1. Okay? And so when we talk about whether correlations are high or not, we want some notion of distance to be involved. So exponential decay of correlations, you have some family of graphs. And then you have constants A and B, and positive. And we say that this model on this family of graphs exhibits exponential decay of correlations if, let's say, the absolute value of this 2-point correlation function is at most a e to the minus b distance in the graph between u and v. Okay. So this is a notion of exponential decay of correlations. Notice you really need to define this for like a sequence of graphs. If I give you one graph, you can always make this true by choosing A and B appropriately. But what's going to be interesting is if we take like some infinite sequence of graphs, like all the possible finite boxes in ZD. Okay, good. Okay. So now we come to defining phase transition. And I'm going to give you 3 different definitions. And in many situations, they coincide, but they're not equivalent. So you can definitely come up with situations where they disagree. And so they really are different definitions. Good. And the number one thing to keep in mind is that a phase transition is not a phenomenon that occurs in one finite graph. So if you give me your favorite graph, and even the graphs I simulated, that's not a phase transition. That's just one graph. Maybe it was, I don't know, 40 by 40 grid. No phase transition can occur on a 40 by 40 grid. Instead, a phase transition is a phenomenon that occurs in an infinite graph, on one hand, or in some infinite sequence of finite graphs. And depending on the definition, these will make sense. So phase transition. So for the, okay, so let's start with some definitions that are a bit easier to grasp. So one, let's say we have an infinite graph G, and this should be amenable. So if you don't know, amenable just means that the boundary size of a set can't be too big. Okay, there's, like ZD is amenable. Like if you take boxes, the boundary gets small. Whereas like an infinite tree is not amenable because no matter what set you take, the boundary size will always be comparable to the number of vertices in the set. Okay, so the definition I'll give you now only makes sense for an amenable graph. What we want to do is define something called the pressure Okay, and it's a function of your graph, so PG, and your parameter in your model. And it's going to be the limit as some finite graphs tend to your infinite graph G. And I'll tell you what this means in 1 second. 1 over the number of vertices in these finite subgraphs, log z lambda n of beta. Okay, so we're looking at partition functions of finite graphs. That's perfectly fine. We defined what a partition function was. We're taking the logarithm and then dividing by the number of vertices. And what this means is that these should be increasing sequence of subgraphs whose boundary size divided by the volume or the number of vertices vanishes in the limit. So boxes in ZD is perfectly fine. And you can show that this limit exists and doesn't depend on this sequence. Okay, so this is the pressure. And remember, like we said, that derivatives of log z capture all this information about the cumulants of the energy. So you can imagine that the pressure actually has a lot of information in it in this limiting sense. So the first definition of a phase transition is a phase transition occurs at, let's say, beta critical if PG of beta is non-analytic at beta critical. Okay, so as a function, like in the complex sense, if it's not an analytic function, then we say a phase transition has occurred. So there's lots of different ways to be not analytic. You could have like a discontinuous, first derivative or second derivative or something like this. If you've heard the term first order phase transition, it means that the first derivative is discontinuous of the pressure. Second order phase transition means the second derivative is discontinuous. But there's other ways to be non-analytic. But this is definition number 1, and it really is about how the partition function changes as you change this parameter beta. And this makes sense for, say, ZD. This is perfectly fine for ZD. But as I said, if your infinite graph was like the infinite deregular tree, this definition doesn't make sense at all, because we can't define this limit. OK, that's definition number 1. So definition number 2 is in terms of correlation decay. We say a phase transition. OK, and this actually could make sense for either an infinite graph G or an infinite sequence of graphs, infinite sequence of finite graphs. Let's say Gn. A phase transition occurs at beta critical if we have exponential decay of correlations for beta less than beta critical, and we do not for beta greater than beta critical. Okay, so if you are in some parameter regime where you have exponential decay, either in your infinite graph or your infinite sequence of graphs, meaning there exists these constants, so you have this exponential decay of the 2-point correlation function, but then there are no such constants after beta critical, then we say a phase transition has occurred. Okay, and so you can imagine in the pictures I showed, the simulations, okay, it's hard to see why a phase transition according to definition 1 might have been in evidence in the pictures, but it's very clear why something like this is happening. In the pictures on the left, while things align close, far away, there seems to be very little correlation. Whereas on the pictures on the right, somehow the correlations don't decay at all. we picked pink as the big dominant state, and then it gives you a much higher chance that some vertex as far away as you want was also pink. So this is definition number 2, and this works perfectly well also for something like the infinite tree. Yeah, there's a question back there.
Where in the definition of pressure did you use amenability?
That this limit exists and doesn't depend on the sequence. So if you take a tree, the boundary contributes something macroscopic to log z, and then the limit won't exist, or it would depend on the sequence that you chose. So the fact that I can define this relied on that. Yeah. OK, good. That's definition 2. Definition 3 is a bit trickier, but it's kind of nice. And so I'll take a little bit of time to define it. Yeah.
First one looks like it could happen in multiple places. Second one sounds like maybe
Yeah, so okay, that's a very good question. So I swept this under the rug. I was pretending as if you can only have either no phase transition can ever occur, or there's a single point at which it occurs. Actually, both of these, you could have multiple occurrences. And so really what I should be saying here is, for beta in a little window below beta critical and beta in a little window above beta critical, because there are models where you have exponential decay, not exponential decay, and then exponential decay again. Basically, anything bad can happen. Yeah, so that's the truth. You can imagine here that you could have multiple points where you're non-analytic, for sure. OK, so definition 3 is about infinite volume Gibbs measures. And so here we have G as an infinite graph. And now I want to define the hardcore model on my infinite graph. I want to define the hardcore model on Z2, or the easing model on Z2. But the definition I gave you was about summing over all configurations and dividing by this sum. Of course, that doesn't make sense. Z is infinite. So how do you define what it means to be a Gibbs measure on an infinite graph? And this is, it's a really beautiful approach called the DLR equations, Dobrushin, Lanford, and Ruel. And they came up with this notion in the 60s and 70s. And it's about how do you define what it means to be a Gibbs measure. So we have, let's say we have, OK, so we have omega, let's say it's 0, 1 to the v. So this, again, v is now infinite. We still have a state space. You can still talk about assigning 1s and 0s to this infinite graph. And we have some probability measure, mu, on omega. Okay. And so I want to tell you what it means for mu to be a Gibbs measure with the given specification. So specification for hardcore would be like the lambda parameter. For easing, it would be the beta. It tells you the parameters of the model. And now I just want to say, you give me this probability measure on this infinite state space. What does it mean for it to be a Gibbs measure? And so what does it mean? So what you do is you imagine here, OK, this is supposed to be the infinite graph. So there's no boundary, but just to say that's the picture. And you want to pick a finite subset of this graph, capital lambda. Maybe it looks like this. And then you want to condition on the values of your spins on the boundary. So you have this measure mu. It's not defined like I defined before. It's just some measure you're giving to me. But now I'm conditioning that the values on this boundary are something, anything. And then I want to look at what's the measure induced inside. And on the other hand, I could have just made a finite graph that has the same shape of lambda. And I could put boundary conditions on my Gibbs measure. So this is a finite Gibbs measure with boundary conditions. So what do I mean by boundary conditions? For hardcore, I just mean I say this vertex is definitely in the independent set. This vertex is definitely not in the independent set. Easing model, I'm saying this is a +1, this is plus, these are minus, minus, minus. And so in the setting where I defined the Gibbs measures before, you just put an indicator in your sum that the configuration agrees with the boundary conditions. And you can perfectly well define this finite probability measure. And so what does it mean for mu to be a Gibbs measure? It's that this conditional measure of the infinite volume measure exactly agrees with this finite way of defining things for every finite lambda and every possible boundary condition. Okay? And if you do, then you are a Gibbs measure with that specification. Okay, so that's the DLR approach to infinite volume Gibbs measures. So in some generality, there always exists an infinite volume Gibbs measure mu g. Okay, as long as your model is nice enough, like you don't have any problem of like not being able to find any configurations or something. There always exists one, but the question is it unique? So are there two different measures mu, like mu1 and mu2, both of which satisfy this property for all sets and all boundary conditions, but are actually different measures, meaning that some functions have different expectations under these measures. And that can actually happen. And so the third definition of phase transition is it's a transition between uniqueness of the Gibbs measure and non-uniqueness. Okay, so let me just give you a rough idea of how this could possibly occur. One thing I could do is, so there's a different way of constructing infinite volume Gibbs measures, which is taking like weak limits of probability measures on finite subgraphs. And so I could take some sequence of boxes in ZD, getting bigger and bigger. But all along, maybe in the easing model, I put +1 boundary conditions on these boxes. And then I could do the same thing, but I put -1 boundary conditions on these boxes. And then I could look at, what is the set of weak limits of these probability measures as these boxes tend to infinity. And, one thing you could ask is, well, if I put +1 boundary conditions on this box, it definitely, because I favor monochromatic edges, it makes it more likely the origin is plus. Okay, so in each of these, the origin is a little bit more likely than 50% to be plus. But does that effect decay or not as the size of the boxes tends to infinity? If that effect doesn't decay as the size of the boxes tend to infinity, then whatever measure I get as a limit, the origin will have 53% chance of being a plus. But then if I put minus boundary conditions on by symmetry, the origin has 53% chance of being a minus. And so I actually got two different measures. And so that's definition 3. Is there more than one possible infinite volume Gibbs measure that you can obtain for this specification? And so again, this really is a property of infinite graphs. But this you can just as well define for, say, the tree or ZD. That question?
When the phase transitions well defined for all three definitions, when do we expect them to coincide?
Sometimes, yeah. For easing model, we know on ZD, we know they coincide. But you know, it's hard work. Like, I think the hardest one to prove there is that you get exponential decay of correlations as soon as you're below the non-uniqueness point. For hardcore, we don't know this. For hardcore on Z2, we don't know that they coincide. We don't even know that there's just one phase transition. And it's not always the case that they should coincide. So you can have models where you have a phase transition where correlations go from exponential decay to polynomial decay of correlations, which means there's a phase transition in definition 2, but you still have uniqueness of Gibbs measure. So yeah, so it's complicated.
So in this third definition, there is no dependence on beta?
Sorry, so what do I mean is a transition as beta changes. So, you know, for small beta in the easing model, there's a unique Gibbs measure. But then when beta gets stronger, remember, beta is controlling how intensely you care about monochromatic edges. If beta was infinity, of course, there would be two different infinite volume measures, the delta mass on all plus and the delta mass on all minus. But the question is there a finite beta where you see this change? So if you don't know, the story of the easing model is kind of funny. There was a physicist named Lenz who gave his PhD student the problem of understanding magnets. And he defined the model for his student easing, who did it on Z, on the one-dimensional grid. And easing proved that there was no phase transition. And so then he said, aha, I got my PhD, I'm done. There's no phase transition possible in these models. But it was called the easing model. And for a while, it was not known whether you could have a phase transition in higher dimensions. And it was controversial. I think they took a vote at some meeting, and there was like, you know, I don't know, 30-70 vote. But then eventually it was proved by Piles that there was a phase transition in dimensions 2 and higher. So it's not at all obvious. I think one of the exercises for you is to show that there's no phase transition for 1D hardcore. Yeah, question? That's a good question. Maybe decay of correlations. Yeah, because this whole notion of DLR equations didn't exist then. Yeah. OK, and that's the end of time. So see you in the exercise session or tomorrow morning.